Among the billions of stars, and over 100 billion planets that dot our Milky Way, lies the intriguing possibility that intelligent life forms might exist beyond our blue planet. This isn't mere fantasy. It's a question science seeks to answer. And today we will dive into the unknown and explore the potential for intelligent life on other planets. In our previous explorations, we delved into the Fermi paradox, the puzzling contradiction between the high probability of extraterrestrial civilizations in the universe and the lack of evidence or contact with such civilizations. But today our focus shifts. We're turning the telescope around, contemplating not just if intelligent life exists out there, but how we might bridge the cosmic distances to find it. We will examine the emerging technologies and theoretical pathways that could one day propel humanity across the stars. Imagine the scenario: humans setting foot on a distant planet, becoming the very aliens we've longed to discover. The idea is not just thrilling, it reshapes our understanding of our place in the universe and underlines the monumental first steps we're preparing to take towards making interstellar travel a reality. Within the confines of our own solar system, the quest for life beyond Earth takes a more grounded approach, literally.
Setting 1012, that gives me
While the prospect of encountering intelligent life forms within our celestial neighborhood may seem remote, there is hope of discovering evidence for past or existing microbial life on planets and moons closer to home. Mars, with its ancient river valleys and lake beds, has long captured our imagination as a potential cradle for life. Yet it's not the only body in our solar system that holds promise. Jupiter's moon Europa stands out as a particularly intriguing candidate in the search for extraterrestrial life. This ice-covered world is slightly smaller than Earth's moon, with a diameter of about 3,100 kilometers. It orbits Jupiter at a distance of approximately 628 million kilometers from Earth. Beneath its icy shell, Europa is believed to harbor a vast ocean of liquid water, possibly twice the volume of Earth's oceans, making it a prime target for astrobiological studies. The Europa Clipper mission, poised for launch in the coming years, aims to shed light on this icy moon's secrets. Its main scientific objective is to determine whether Europa's subsurface ocean could offer habitable conditions for life. By conducting detailed reconnaissance of Europa's ice shell and underlying ocean, the mission seeks to assess the moon's habitability, studying its composition, geology, and the potential for water ice plumes that could offer direct samples of the ocean below. However, exploring Europa is fraught with challenges, not least of which is the moon's harsh radiation environment. This radiation can incapacitate or destroy a robotic lander within hours, even with robust shielding, making the prospect of human exploration with our current technology an elusive goal. With today's technology, a manned mission to Europa would be close to impossible, not only because of the vast distance but also due to the lethal radiation environment. This radiation would pose a certain lethal risk to any crew daring to venture to Europa. So if exploring the potential for life, even within our own solar system, presents such an enormous challenge, how can we dare to imagine that we will one day explore the stars in our galaxy? There are two solutions for this. The first one involves designing and building what is called a generation starship. This is a hypothetical type of interstellar arc starship that travels at sublight speed. Since such a ship might require hundreds to thousands of years to reach nearby stars, the original occupants of a generation ship would grow old and die, leaving their descendants to continue traveling. As you might imagine, there are several problems with this solution. If such a starship takes several generations to reach its destination, it's plausible that more advanced technologies could be developed on Earth during the journey. These new technologies could potentially render the starship obsolete, or even enable faster spacecraft to reach the destination before the generation starship. This paradox raises questions about the viability and efficiency of generation starships. So this leaves us with the second solution: improving propulsion systems. NASA has hired Lockheed Martin to design, build, and test a nuclear-powered rocket for space travel. The technology could speed up a manned trip to Mars from the current 7-month minimum to as few as 45 days. A nuclear fission reactor would power the rocket's engine for nuclear propulsion. A nuclear propulsion rocket can theoretically achieve a maximum velocity of about 22 kilometers per second. However, there are designs that propose even higher velocities. For instance, a certain design using magnetic fields to channel hot gas out of the engine could theoretically reach speeds of up to 197,950 kilometers per hour, or close to 55 kilometers per second. But even with this speed, that is not in existence yet. The time it would take for a nuclear propulsion rocket to reach Alpha Centauri is approximately 26,000 years. You see, the problem with space is that it's too vast. However, in the concept of nuclear pulse propulsion, it's suggested that a spacecraft could reach a velocity of approximately 13,411 kilometers per second, which is about 4.5% of the speed of light. This would theoretically allow a spacecraft to reach the neighboring star Alpha Centauri in 100 years. There are theoretical concepts for spaceships that could potentially reach speeds up to 10% the speed of light. One such concept is the use of solar sails. Another project, known as Breakthrough Starshot, aims to develop a nano spacecraft that could travel at 20% the speed of light. This project proposes using lasers to propel a tiny spacecraft to our nearest star system, Alpha Centauri. However, this concept faces challenges such as the survival of the spacecraft's electronics in the harsh conditions of space over a long duration. But for the moment, at least theoretically speaking, this project remains our best shot for reaching the stars. It is a project by the Breakthrough Initiatives to develop a proof-of-concept fleet of light-sail interstellar probes. The fleet would have about 1,000 spacecraft. Each one, called a starship, would be a very small centimeter-sized vehicle weighing a few grams to be capable of making the journey to the Alpha Centauri star system about 4.3 light-years away. A flyby mission has been proposed to Proxima Centauri b, an Earth-sized exoplanet in the habitable zone of its host star, Proxima Centauri, in the Alpha Centauri system. At a speed between 15% and 20% of the speed of light, it would take between 20 and 30 years to complete the journey, and approximately 4 years for a return message from the starship to Earth. The quest for alien life takes an exciting turn with Proxima b, an exoplanet in the habitable zone, where conditions might be right for water to exist in liquid form. Its discovery has ignited the imaginations of scientists, offering a glimmer of hope that we might not have to travel vast distances across the galaxy to find signs of life. However, finding intelligent alien life on Proxima b, our very first stop, is perhaps unlikely. Therefore, we turn our gaze to Gliese 667cc, another compelling exoplanet in the hunt for extraterrestrial intelligence. Given that this exoplanet is approximately 23.6 light-years away from Earth, with our theoretical spaceship traveling at 20% the speed of light, we would reach it in 118 years. Gliese 667cc is classified as a super-Earth, meaning it is larger in mass than Earth but smaller than the ice giants Uranus and Neptune, potentially offering a rocky composition with a more substantial atmosphere. This categorization stirs interest because its position within its star's habitable zone suggests it could maintain liquid water on its surface, a key ingredient for life as we know it. The intriguing characteristics of the planet make it a prime candidate in the search for extraterrestrial life, proposing a world where conditions might just be right for life to flourish, possibly even intelligent life, under the right circumstances. Our next stop is TRAPPIST-1e. Located about 40.7 light-years away from Earth, it would take more than 200 years to reach it, with our theoretical spaceship going 1/5 the speed of light. TRAPPIST-1e orbits within the habitable zone of its ultra-cool dwarf star, where temperatures could allow for liquid water to exist on its surface, a crucial factor for life as we know it. This Earth-sized planet is part of a fascinating system where several planets have the potential for water. The prospect of alien life on TRAPPIST-1e is compelling due to its Earth-like qualities and the possibility of harboring water in liquid form, offering a tantalizing scenario for the existence of life. With its relatively close proximity and promising conditions, TRAPPIST-1e stands as a beacon in our quest to discover life beyond our solar system. Now we set our cosmic sail to Kepler-186f, an Earth-sized exoplanet orbiting within the habitable zone of the red dwarf star, Kepler-186. It is located about 580 light-years from Earth in the constellation of Cygnus. It is so far away that if intelligent aliens had a hypothetical telescope pointed towards and piercing Earth's atmosphere, they would see the Earth in the year 1444, potentially witnessing the Americas before the Europeans did. This thought-provoking perspective underscores the vast distances and timescales involved in the cosmic arena. Kepler-186f's significance lies not just in its Earth-like size, but in its position within its star's habitable zone, where conditions might be right for liquid water to exist on its surface. The planet orbits a type of star known for its longevity and stability, which could provide a consistent environment for the development of complex life forms, should the right conditions exist. However, the sheer distance poses a tremendous challenge for exploration and study, as even with our hypothetical spaceship traveling 20% the speed of light, it would take us 2,900 years to reach it. As our journey through the galaxy extends, the distances become even more staggering, bringing us to Kepler-22b. Orbiting comfortably within the habitable zone of its star, Kepler-22b is located 640 light-years from Earth. This exoplanet captivates scientists and dreamers alike with its potential to harbor life. Its size, possibly larger than Earth, hints at a world with extensive atmospheres, vast oceans, or even life-supporting conditions. The mere possibility that Kepler-22b could support life tantalizes the imagination, suggesting scenes of alien landscapes and ecosystems unlike anything we've encountered. However, even with our hypothetical spaceship traveling at 20% the speed of light, a journey to Kepler-22b would take an astonishing 3,200 years. Such timescales push the boundaries of our current understanding and capabilities, making the voyage to Kepler-22b, and indeed any interstellar travel, a daunting challenge. These vast distances underscore the necessity for breakthroughs in space-traversing technology. Concepts like the Alcubierre drive, a speculative idea that proposes faster-than-light travel through the manipulation of space-time, offer intriguing possibilities. Although such technologies remain purely theoretical for now, they ignite the imagination about future exploration. We'll delve deeper into this topic and the potential for warping space to achieve faster-than-light travel in another video. Thank you for watching.